it's a pleasure to introduce Elkim Roa. He's given a talk entitled Low Energy Always On Subsystem and Circuits Enable Security in RISC-V Based SoCs. Elkim Roa received its bachelor degree from Universidad de Santander in Bucaramanga, Colombia in 1990, the master degree from University of São Paulo in 2003, Brazil, and the PhD degree in electrical engineering from Purdue University in 2014, where he was a Fulbright scholar. From 2014 to 2016, Elkim was with Rambus Incorporation, where he was engaged in high-speed SerDes front-end design. Currently, he is associate professor at Universidad Industrial de Santander, Colombia. His research interest includes circuits and VLSI design for security, front-end circuits with high-speed interfaces, and low-energy and efficient computing. So, Elkim, you can start your talk. I will stop my camera.
Thank you so much, Professor Fernando, for the kind introduction. I will also turn off the camera, so we'll improve the bandwidth and also the size of the screen. Okay, so this talk is called Low Energy Always On Subsystems and Circuits Enabling Security and in RISC-V based system chips. This talk is on behalf of a team. So this is not just a talk. All the content here is produced by students. I'm just part of, just a professor who is just giving the talk, just passing all the content the students have done. So here, so I will try to show the team, and then afterwards I will try to discuss the 3 different system chips that have been developed here in Colombia, where we have put some power management circuits and also all-in-one circuitry and security circuits to improve precisely what Victor just mentioned, IoT-based sensors. So here is the team. The team is mainly composed by grad students. We have 5 PhD students currently and 7 master students, and usually we have around 8 to 10 students in the last year, so senior electrical and electronic engineering students. We have also an academic collaboration with the University of Cambridge, University of California, Berkeley, Politecnico de Torino, and the University of Electronic Communications in Tokyo. So actually, most of the work that I'm going to present is being done in collaboration with these universities. Also, we have an industry collaboration with Sci-Fi Inc., which is a company currently placed in San Mateo, California, which is founded by the founders of RISC-V, and LogRISC, which is also a company founded by Raspberry Pi founders in England, and Symbiote DA is a company mostly focused on formal verification. And we are kind of proud of this kind of internship program. We have currently we have 2 master students and 2 PhD students overseas doing internship. This is something that we do. We try to do it continuously here in our group, where all grad students go to internship programs. So now we're going to talk about the 3 different microcontrollers that we have designed here in Colombia. These 3 different microcontrollers, we named them with bird names, actually endemic Colombian names, endemic Colombian birds. So the first one, the one on the left, the 2016, we call it Turpial, and it was the first microcontroller using RISC-V instructions. Actually, the PAL was in 2015, and in 2016 we did the measurements, and we get some success from those measurements. In 2017, this was a kind of collaboration with Sci-Fi. This is another microcontroller. It's capable of doing cache, and it's also capable of doing 200 megahertz frequency prediction. In addition, we add a lot of instances for power management units. 2018 chip is a little bit smaller than the 2017. Doesn't go all the way to 200 megahertz, go to 40 megahertz, but we add additional security circuits and entities in order to be more capable for low energy sensors of IoT. So we are going to talk about these three different microcontrollers and all the instances that we put there, mainly the low energy circuitry and also the security entities. So here we have Turpial. As I say, we codenamed them regarding the endemic bird names in Colombia. And here is a picture on the right of the die of the microcontroller. And in the picture on the left is the board that we use to exercise the microcontroller. Something interesting here is that although we don't have much of the let's say peripherals that current microcontroller has in this, we put the data converters, capable data converters, ADC 10 bits that is capable to go 10 megasamples, and also a digital analog converter with 12 bits. And we were able to do a lot of tasks with this microcontroller, similar to the ones that are commercial based in MCU, like the ARM MCU. This is just a summary of some of the performance. Something to highlight here is the core dynamic power. Measured at 100 megahertz, we were able to reach 160 microwatts per megahertz. This measurement is done in a 3-watt load condition. All the program is running in SRAM. So this kind of performance is similar to the one in commercial ones, like in this table. So although it's not a fair comparison, because here all these are commercials that have not just the circuitry, but also the debugging capability, testing capability, that might add an additional power. This tells us the capability of the microcontroller. So this microcontroller is around M0, like I said, M0 and M0 plus performance microcontroller. So similar to the ones in for instance, in the boards like in the Arduino Zero, or in the boards that NSP brings for IoT. And we also are proud of the software tooling that we did for this. We did all the environment, the development environment for the microcontroller were on JavaScript in order to be run in a web browser. So here is, for instance, running in a Chrome. So you can even program the microcontroller using assembly, just RISC-V instructions. Actually, this was one of, as I say, was one of the first microcontrollers in RISC-V base. So a lot of people that are now is using RISC-V base instructions. This platform was the first one that they use in order to run RISC-V based programs. We are also be able to run to write in C. We also are able to write in Blockly and also in Arduino. So, for instance, here we show that a high school student will be able to use like a Scratch-based program language. In this case, using puzzles. We port Blockly, which is a Scratch port from Google. It's called Blockly. We ported to be able to use it in our environment. So by doing our own microcontroller, we were able in few weeks try to do drivers to compile in C, in Blockly, and even in Arduino. And Sonan method that is fun about this is that in 2016, when we were showing this in the RISC-V workshop, they were there, Federico Musto from the president of Arduino, and he told us that by that time he couldn't do that because Ahmed, who who was the owner of the Chisel Arduino board, they haven't delivered the drivers in order to do this. So this is one of the advantages of doing your own hardware. We also add a live programming environment. So we put these boards on video cameras, so people were able to connect to the boards and program them overseas. It was a time at the beginning, after the RISC-V workshop, there were 1,000 people with tickets in queue in order to get access to the boards. So also we kind of generate a lot of noise in the news, and thanks to this microcontroller in 2016. We also went a little bit further. We tried to develop puzzle boards for little children in order to use it instead of an Arduino. So we use these kind of boards with our own microcontroller. So we tried to design the boards as a Arduino, as a puzzle pieces. As is here, actually in the puzzle piece on the right, this microchip, this epoxy. Under the epoxy is a die of our microcontroller. Now I'm going to talk about Toucan. So Toucan is a microchip, a microcontroller designed in cooperation with Sci-Fi. So in contrast to Turpial, so Toucan is more capable. Is cacheable, so it has cache, and it knows, although it's also 3 stages, it has more RAM. It has the instruction cache also. In addition, it has additional power management units in order to control the voltage and monitor all the power of the circuit. So in this project, the work of the Universidad de Santander was try to develop all the peripherals, including the power management unit. Here is kind of the architecture of the microcontroller. Further on, I will try to discuss the power management units and this always-on circuitry that we develop here. So now we are going to talk about the last microcontroller, GetInE. GetInE, in addition to the analog peripherals and the power management unit, we add acceleration, crypto acceleration, and we also add additional security entities as true random number generators and also PAF, physical electronic function. So this is GetInE. It was measured in 2017 and measured in 2018. So on the left are the different, so here we are showing on the left, the upper left, the layout of the chip. On the right, the amoeba, so describing what is under all those metals. And the picture of the die, also the picture of the package. And the board that we use to exercise the microcontroller. So this is the block diagram. As I said, we add directly to the core of the microcontroller AES acceleration, AES 128 bits acceleration. We also add a PAF, which is embedded in the NVRAM, and we also add a true random number generator. So now let's talk about the always-on circuitry and the power management unit in a little bit more detail. So this is the block diagram of Toucan. So this is all that is highlighted here in gray is the power management unit. So a power management unit requires to have monitors and a kind of isolated state machine that is capable to check those monitors and also to check the loads in order to decide for the clock or even to drop loads by dropping regulators. So let's first talk about the oscillator. So if there is an always-on circuitry, so you will need circuitry that is so low power in order to be always on. So imagine a sensor that you are going to drop to measure temperature, but that you are going to measure temperature, let's say, every hour. And at the end of the day, you will send that data through a server. So and you take, in order to measure the temperature, you might take less than 1 millisecond in order to measure the temperature, and in order to send the data, because it's going to be a small payload, you might need around several tens of milliseconds. But in order to, in the rest of the time, you need to be sleeping. But you need to be sleeping, but with kind of a little bit your eye open, right? So you need to have an oscillator, right? If you are waking up every time, like every hour, so you will need a real-time oscillator that is capable to have a low energy consumption, but also to have a fast startup. So here we are talking about the different operation modes that kind of my system on chip require in order to be a low, or to be always on, or to be using an always on sensor-based application. So on the left is the active operation. So all the blocks that are highlighted in blue are the digital blocks, and all the purple blocks are analog blocks. So just imagine that currently you are doing an operation, or the microsystem on chip is doing a high performance operation where you need all the high frequency oscillator operating, and you also need everything connected on in order to do some tasks. For instance, you are right now trying to send data through Wi-Fi or through any network. But also when you are going in a sleep mode, let's say in one of the deep sleep modes, you will need to turn off all the blocks and just leave the required blocks in order to wake up, for instance. So, and also to monitor the battery, or to monitor let's say the power source. That could be a solar panel, or could be a piezoelectric harvester. So in this case, we have low frequency oscillators. It could be a low frequency crystal oscillator, or it could be an RC oscillator. Usually most of the shelf, or the commercial of the shelves, have both of them, but you will want accurate oscillator in order to do a real-time operation. You might use low frequency crystal oscillators. And also you will need to monitor the battery and the power source. So a burnout detector and a power research is required in order to do a proper power up operation. So let's assume that now we are going to wake up with the crystal oscillator, with a 33 kilohertz crystal oscillator. So usually the energy required for a crystal oscillator in order to start up is around 15 nanojoules. So you know that in a crystal oscillator, the quality factor is so high, so that's why it requires a lot of time in order to start up. So that's why the start energy is quite high. On the other hand, we presented a low energy startup oscillator in CACCG 2019, where this RC oscillator consumes just 70 picojoules of the start energy, with the accuracy required for a wake-up timer. So just gonna try to indicate what we have done. So with this, compared to the crystal oscillator, we were able to reduce the energy 10 times compared to the crystal oscillator, and we were even 10 milliseconds faster. So the final energy reduction was even larger. So how to go to do a low strategy in a classic RC oscillator as the one shown here? So there are two options, right? One option to do a low power consumption circuit, and also to have a short startup time. So how to do both? So in this case, we focus on both. We focus on short startup time, and we focus on low power consumption. So let's first try to understand what is startup time. So the startup time, the definition of startup time is the transient time that is required for the oscillator to get a frequency settled within 2%. So that will be no easy for a crystal oscillator, since it has a high quality factor. So it will take a lot of cycles in order to settle within that value of frequency. Whereas in our RC oscillator, it will depend how do you manage to do the startup. So if you check in a regular RC oscillator, the RC oscillator will be determined, the time of the startup will be determined by the voltage reference. So if you are doing a low energy voltage reference, that means that you are doing a high impedance current branches. So for the time constants will be high. So the time to go to a determined defined value of voltage reference will be so large. So it will be a slow startup. So the only way is try to decrease this time. So how to do this to decrease this time? So the only way is we cannot use regular voltage reference. So one way is to use a switch capacitor. We use a switch capacitor reference that settles after the first cycle. So here we can kind of show how it works. So here is uncharged. So when we start the capacitors that are not still not charged, and then we kind of go and charge all the capacitors in series, and as in this case, they're in series, right? So we have here this capacitor will be charged by 1/3 of the VDD, which is based on the value of the VDD, is the value that we require, and then we put the capacitors in parallel in order to be the voltage that we require in this case. So it takes just one cycle to charge the voltage reference. So in that sense, we will have the startup time of this RC oscillator will be about one cycle or even an additional cycle to settle the charge of the capacitor. So we will see this in measurements. So another thing that once we improve the startup time of the RC oscillator, now we went try to see how we can improve the low power consumption. So the lower power, the power consumption is determined by the OTA. In this case, the one that is doing the comparison between the voltage charge in the capacitor and the voltage reference. So for instance, here we are showing that the power consumption of the error amplifier is about 80%. So one way to reduce the power consumption was try to turn off the OTA when it's not required. So we will just turn on the OTA when we need to do the comparison. When we need to do the comparison here when the capacitor is being discharged. So that's going to be a finite time. So we will save a lot of power in that sense. So we will be able to reduce the power consumption about 90% thanks to disconnecting the error amplifier when it's not required. We also add a Schmidt trigger in order to improve that connection. But now the Schmidt trigger is the one that limits the total power consumption. Yeah. Let's go into this slide. So in that sense now, in order to keep improving the energy, so we have to do a trade-off between the hysteresis of the Schmidt trigger and the fast response of the Schmidt trigger. So we were able to do that and achieve the best figure of merit or RC oscillators by 2019. So here is the picture of the RC oscillator. We put two instances of the RC oscillator with the chip, and we did some measurements. Here I just want to highlight that we are a state machine in order to do the tuning of the RC oscillator in order to improve the accuracy of the oscillator. So for instance, here is the field running performance. Here we're showing the voltage constants of the frequency, which is not that cool in field running, and the temperature constant also of the oscillator. Of course, after tuning, the temperature constant improved from 2000 ppm per Celsius to 68 for the case of 30 kilohertz. These are oscillators capable to run from 30 kilohertz all the way to 1 megahertz. So for 1 megahertz, the temperature constant is even better. All the measurements. So here are the results of the startup time measured at nominal conditions. So we went from milliseconds to 200 microseconds for the case of the 32 kilohertz. For the case of 1 megahertz to to around 4 microseconds. So here for different corners of the voltage. So as I mentioned, with these results, we were able to achieve the best figure of merit reported. And we reported this in AES, in Custom Integration Conference last year. Here is a performance comparison compared to previous work. We showed that we get results in performance similar to the ones reported, but even with better figure merit at the end. So now let's talk about the power management unit. So we talk about the clocking. Now let's talk about the circuitry that do the voltage monitoring. So in a power management unit, so here we have the system on chip architecture. Here is the power management unit. It's the one that is in charge of providing all the supply, but also the one that is in charge to monitoring the loads and the voltage and the power supply in order to have a correct operation of the system on chip. So let's focus on the power management unit. As I said, the power management unit is the one that sets, besides the power supply, also sets the clocks and enables the clocks in order to go from different modes. So in this case, we have three different states of modes: active and sleep and deep sleep. So in deep sleep is the state where the system on chip is usually operating. We are showing here that we have 4 different closed sources. We have a high frequency crystal oscillator, we have a high frequency ring oscillator, we have the RC oscillator that is just presented, and low frequency crystal oscillator. So for instance, here we saw kind of how the power management operation works. So let's say the voltage is the battery is fully charged, and it goes from fully charged to kind of discharge, or is start up. So what we need to do is first of all go from high frequency to low frequency, and also start dropping loads in case we are not able to recover the voltage. So here we see that by going to low frequency, we were able to recover the voltage a bit, but again, we might even to get a faster recovery if we need to drop any load. So we were able to drop LDOs in the case of this, in the case of the active or the sleep mode operation. So here is a picture of the microcontroller to the left, and to the right the board that we use to exercise the microcontroller. So here are some measurements of different operation modes. So as you see in the deep sleep mode, we're able to achieve half a microamp. So you see this microcontroller will be able to operate around 5 years in a small coin battery by just doing 1 wake up per day. This is kind of also showing how we go from high speed frequency to low frequency operation, and how we keep dropping loads in order to improve the voltage operation. Here is also a picture showing how we are capable to do power getting of all different instances. So we also have voltage regulators and detectors. So we need a power on reset, and we also need a power on detector. A power on reset is the circuit that does the initial reset for the always on and for the core domains. And the brown detector is the one that monitors the voltage in order to detect any drop of voltage, in order to also recover the voltage as supply value being dropping load or being decreasing the frequency. So let's discuss a little bit about the power on reset. So the power on reset is the circuit that monitors, and we can have different power on resets. For instance, we will for different voltage supplies. This is kind of the common approach right now, where every voltage supply has its own power on reset. It is not easy to design a power on reset with multi-threshold voltage regarding the low operation that is required for the power on reset, and the low energy operation that is required. So it's usually customized for every voltage supplies. So we here kind of propose a multi-layer power on reset where we just measure, we just want one instance all the voltage supplies. So we have a multiple layer voltage power on reset in order to do that. We except that multi-level power on reset, you can put it directly to the load, or you can even put it before the PMU, let's say directly to the main BD. But we saw that the best results are when you are just sensing directly the loads. So it's not easy to capture the values of the BD before the local regulators. So it's better to have all voltage monitors directly to the voltage to the local voltage supplies. So here is the proposed model multi-layer power on reset. We use different approaches in order to have low current operation. For instance, here we show that we are using net transistor, which is currently a well-used technique in order to decrease power. So this is definitely working on near threshold on sub-threshold operation. We also have a mode set in order to check these values. The problem with this kind of circuitry is the low swing at low temperature. So we need to have kind of a trimming circuitry, digital trimming circuitry, in order to improve that once we have the measurement results. So here is, for instance, the one that we instantiated in Tucán. We instantiated global and local the power on reset. So here we're showing a local power on reset and a global power on reset. Here is the layout of the circuit. This work also was presented last year in ICCCS. Here are the measurement results for the global power on reset, showing the different level ranges that the power on reset can operate. So we also have the Brown detector, which is the kind of the voltage drop monitor of the circuit. And again, we can have a Brown detector before the PMU or before the main LDO, or after or even connected to the local LDOs. We kind of see that the operation of the Brown detector is better when we have them connected directly to the local voltage supplies. So in that sense, we are able to have better monitoring of the circuit. For this case, we are showing a global Brown detector where we are detecting the drops directly from the power management unit from the main LDO. But as I mentioned, we also have local BODs, but here I'm just showing the global BOD. In this case, we are showing also that we are able to place local BODs in order to detect with more sensitivity drops and decide based on those drops which loads we have to drop. So here we start, for instance, showing how different voltage domains start dropping or start having kind of a crashing. Let's assume that we are turning and we have low battery, but we are turning a high-speed oscillator. So all the domains are going to be or start crashing. So you have to save, for instance, one of the things that first you have to save is the memory. You have to save the memory in order to the core to to continue. So you will need to take decisions. Those decisions, in order to take those decisions, you need to have monitors in order to operate. Here is the proposed multi-threshold burnout detector. We are not showing details of the circuit here, but this is a system-level block diagram of the burnout detector. We also have trimming circuits in order to improve in case of purity variations. So the proposed multi-threshold burnout detector is here shown here in the left. When we are having a drop in the burnout detector, we will be able to capture that dropping because we have different levels in this case in the voltage reference. And it depending the value of the VDD we are checking, we decide which multi we are connecting. So all this digital operation is also run by the powers management unit. This is kind of a digital intensive burnout detector. Here is the burnout detector placed on Tucan, and it was placed as a blowout burnout detector. Here are some measurements, and the current consumption in normal condition is about 280 nanoamps, which makes the burnout detector suitable for low energy sensitive applications and always on circuitry. So this is the performance comparison with related work. I'm going to speed up a bit. So now let's talk about security circuits and techniques. So we add different security circuits in order to improve or to decrease the vulnerability of the system on chips. So first of all, we add a true random number generator that is required for different algorithms like AES and all other applications, and even for starting the GE. So in this case, we are using a conventional architecture for the a conventional architecture for a true random number generator is to use an interpret source, then digitize that source, say count it, sample it, and do some post-processing to improve the quality of the randomness of these numbers. So usually is a processing that truncates or compresses that data. So the current approaches and challenges for random number generators is one is data stability and the other one is using Green oscillators. These are kind of the most common techniques to generate the interpret source. But the problem with this kind of two circuits is that they have purity sensitive, and then you will require a lot of calibration bits in order to improve the quality of the numbers being generated. So here we use similar entropy source to the one published in ICC 2014, where instead of just using random, using just jitter, we kind of do a trigger with nonce here. So by doing a trigger, in this case, simultaneously to these three different stages, the oscillator is gonna start oscillating at 3 times the frequency, and there is an undetermined time where the oscillator, after this trigger ends, there is an undetermined time to become again a conventional resonant oscillator. That means to come back to a natural frequency in this case to reduce 3 times the frequency. So in this case, we are showing different results. So here we are operating at 3 times the frequency, and then it goes and settles to the natural frequency. So the idea is try to count how long it takes this time to settle, and based on that time, we generate random numbers. So we are also add different paths. So we add short paths and long paths in order to improve the random number generator. And we kind of measure the circuit. We also put it into CAN. We measure the circuit and get this result. These are raw measurement results. As you see here, these are different results for fast throughput, medium throughput, and slow throughput. As you can see, there is no normal distribution on those results, so you have to do some kind of post-processing. So the post-processing that we implemented, we truncate the number of bits. So in this case, we went from 14 bits to 10 bits, and we were able to pass all these tests to get better. Here is decreasing the number of or truncating even more the number of bits, and we even get low words. So we decided to truncate to 10 bits, and with that we were able to pass for all the NIST tests. So here are more measurement results for different throughputs, and just showing the performance. So we also implemented a physical and clonable function. So the idea of the physical and clonable function is to use in this case we are using a floating gate non-volatile RAM. So usually people try to put a seed that is hiding in a non-volatile RAM. So how come we are using a non-volatile RAM in order to generate a physical a number that has to be hidden? So the difference here is that this number is going to be hidden even for the user because it's going to be generated through the process. So when the wafer is being fabricated, so there will be charges injected during fabrication. Those charges will be injected asymmetrically. So there will be some, in this case, floating gate that will be receiving more charges than the other. So then through the sense amplifier latch, you will be able to have a flick bit that once it gets sent, it can be amplified or even can be endured in this NVRAM. So our proposal was try to measure all this raw data, and once we had that raw data measured with the sense amplifier, we kind of read the data, post-process the data, and again come back and write back in the NVRAM the values that have better randomness. So in this case, we implemented NVRAM, a macro NVRAM, and with that macro NVRAM, we were able to measure after the fabrication what was the data stored according to the injected charges through fabrication. So with that, we get this kind of growth in unstable bit percentage. So we get from 50% all the way to 0%. So as you know, this is kind of a good number, but it's kind of an average number for raw unstable number of bits. This was measured across 8 chips in typical conditions. We were able to get this data and normalize it through Hamming weights, and we can see that the mean value is around 50%. So we add post-processing stage where we deal with the kind of a big count decision, and then this is different than majority voting, where we just go in a different way in order to get better precision. And once we get decisions as a 0 or is solved as a high value, we decided we write back using the programming mode of our NVRAMs. So we program back using tunneling the floating gate. Now we have a path number already stored. With those measurements, with that data, we were able to get a reconfigurable path with 0% instability after being stabilized. So this work is being actually was accepted in ISCAS and it's going to be presented in ISCAS this year. So the next instance that we implemented was improve or accelerate AES SBox in our system on chip. So here we are adding SBox that is going to be transparent to the programmer. So one of the good things about having now a RISC-V based ISA is that now we have a community, so we have all these compilers and everything. So in this case, we use one type instruction, which is actually a vector instruction, in order to put the acceleration instruction. And in one of the advantages of doing this way is that now when you are compiling using our microcontroller, the only thing you have to add to the compiler is a header, a .h file that indicates that when the AES algorithm is being compiled, go and use the SBox engine, the SBox instruction that is in the header. It's that transparent, so we don't have to go and do any FPGA connections in order to use. So this is the SBox instruction replacement. So we went from this to a fully instruction that could be serial in this case, like the one on the right, which is completely serial. So we can do with three different architectures. We did the serial pipeline operation. So one of the advantages of this one is that we can have low area. And also we did a parallel implementation in order to improve time. And we went a little bit farther in order to improve to improve performance, and we put an SBox with an additional lookup table. All those three were implemented in GetUni, and here we are showing we are highlighting in black all the code with the SBox engine. So you see the SBox engine occupies a little bit more than the yellow or similar the control status register. Here are the results. So we were able to improve power and also energy of the AES algorithm. So we also, for getting new, we also had something additional was to camouflage. So basically, to do camouflage, to do obfuscation, there are two methods. One is structural, another one is physical. The structural is like to add a key or add gates that will require a key or a key value in order to those values to become nominal to the function behind. All the other one is physical. Is try to obfuscate the layout. One that is common is to move the gates around, or in this case, to move the vias around in order to obfuscate the layout. So we are using actually the second one, the physical one. The problem with the physical one, or the one that are reported, they change the layout size, and so they get timing and they get area and also power overhead. So our proposal is try to do a layout that has the similar size. So here, for instance, we're showing an inverter, a picture of the inverter with the layout. So what the attacker usually does is they take pictures of the chip once it's decapped all the way to the metal one, or metal two, and based on the connection, they decide which gates are there. Actually, if you check a standard cell library from ARM or even from Synopsys, let's say from 65 nanometers all the way to 14 nanometers, you will see that those are similar, except that in 14 nanometers and in 28 nanometers, you will see that you have the gates are placed in equal pitch, but the structure, the logical structure is similar. So actually, if you go and check online, you will find tools that are able to, after taking picture, they were able to go they discover which case they have there, and based on that, they get in a list. So what we decided was, let's try to do the obfuscation, but with same size, and we are going to do it with different flavors. So how we generate the flavors was our proposal. So we decided that we are going to use a standard cell generator. So we went through all the nightmare, actually, of generating a standard cell generator in order to use kind of the no-optimized layouts as obfuscated layouts for the CPU. So for instance, when you are in this case, we are showing an obfuscation level of 4, where you put different form layout. So when you are doing synthesis, here is the obfuscation algorithm. So this is on-fly obfuscation when you are doing placement and routing, and synthesis. Actually, when you are doing synthesis, what usually we do in these cases, we go and run the synthesis with the normal standard cell. This is with the cells, with the cell library that is the best performance. Once we get the results of the synthesis, we know what is the timing, what is the critical path, and the critical path we kind of block the critical path and start generating standard cells for the paths that are not critical. If those paths that are not critical become critical, so we start blocking them and blocking the generation of standard cells for those, and so on, until we obfuscate the full. And the generation of the standard cells are also on fly. So we are generating standard cells on fly as the algorithms, as for instance, artisan uses. So we use a regular commercial flow, we use synthesis with regular standard cells, and we do the obfuscation ensuring critical path. Here is just showing that actually this is kind of a part of a major job where a student is doing using SAT and proposing place and route algorithms for the standard message generators. So here is showing how our in-house standard cell generation flow works. We use actually all the standardization is using is an algorithm running C, but all the cells are being generated using skill from Cadence. Here is just showing a little more details how we do these standard cell generations. I'm going to skip that. So here, for instance, is how the obfuscation results. So if you use an algorithm that actually this algorithm that we use is it was provided from Europe, from a university in Europe, and with that algorithm we run it and we detect the ones in red. So these are so for instance we are here detecting these are north. So we are detecting gates north. But as you can see here, these north cells are being not detected. Although they are similar, they're in layout, they are not similar. So that's in a small circuit. So now we did that for different bigger circuits. We did that for a Galois field multiplier, we did that for a key establishment core, and we did that for our RISC-V core. And with that, we found out that we were able to do good percentage of obfuscation. So for instance, here we find out that the percentage of detection was quite low. So in that sense, they will not be able to detect. When you see high percentage is because it's, in this case, it's detecting more number of inverters than the ones that are there. So it's kind of saying that it's still working as obfuscating algorithm. So here are the overhead results. So as you see, in this is area, power, and timing. So the The dark one is area, the green one is power, and the yellow one is timing. As you see, the critical one is power, where we get about 5% of overhead compared, which is kind of okay for some case applications. So this is for the RISC-V based core that we use in Getini. We just get 2%. And that's it. So this is the summary. So just want to summarize that we have developed 3 different systems on chip. Those are all tested, and we have been using those for different applications. We even tested in for industry grade temperatures. With that, we were able to show that some always on circuits idea are working fine, and also some security entities are also working fine, as we showed in the previous slides. So with that, I open the floor for questions. Hello?
Hello. So, Moraes and Elke, can you turn on your cameras? I think the connection of Fernando Moraes dropped. Now he's back. So waiting for this.
Well, thank you.
Moraes.
Sorry, I had problems with nconf. Thank you for your nice presentation. Okay. We have time for questions. So if anyone has questions, I can start with the questions. I'm not seeing my camera. I try to connect it. Okay, I have a question regarding the first part of your presentation. Have you considered, for example, resilient mechanisms as razor, RISC-V to detect faults when you decrease the supply voltage?
Yeah, that's a good question. Actually, razor, kind of a deprecated technique. It's being published, and it's still being published, but actually Intel already said that they are not using any more razor. What Intel does is something similar to this, that they check voltage, but now what they are using right now is actually they move all, if the supply changes, or they try to change also the supply of the PLL. So in that sense, the PLL or the clock frequency also changes. In order to detect those errors on the critical paths, what they are doing is that they are copying these critical paths and putting the same operation and connected that to regulators to indicate the reliability period that what it has to do in order to improve that. So those are kind of techniques more specialized for this kind of processors, for servers where they need high throttle loading. In this case, just recall that these are system chips for low energy sensors. So the throttling of the loading is kind of known. It's not that a user is there is an unknown throttle like in the processor, right? The processor is going to be used in different kind of application, and different cases. In the case of the system on chip, the system on chip will be applied, for instance, for a temperature sensor or for any IoT application where the user will know how to do the throttling. So because they know how to do the throttling, they will kind of program the PMU in that sense. So it's kind of different scenarios for using razor, but razor is not used anymore.
I say it's my question is, if you have implemented some mechanism to avoid errors, so have implemented something like duplication of critical paths, if understood, right?
Yes, as I say, no, there is none for this kind of application. There is no required because the trolling is known by the user.
Okay, we have a question here from the YouTube. There is a presentation question from João Camilo. He wrote, "Thank you for the nice presentation and configuration. Congratulations. Are you thinking to add RF communication features? And what are the future steps for your microcontroller?"
Yeah, so first of all, so we are more research team, so we are not trying to aim to have a final product. So this is, we are more focusing on some areas where lower energy sensor-based systems is required. So we are more focusing on security, also power management, always on circuitry. So we are not thinking on RF circuitry or adding any other circuitry for the future. As I say, we are not planning to go commercial. This is more like a research team.
Okay, let me see. Have you another questions? I have another question, waiting for another ones. For example, ARM used, for example, to protect the memory, the approach called trust zones. Mm-hmm. Are you considering to have some protection at the memory level also?
Yeah, that's a definitely good question. So yes, we are doing. So we are actually, there is a PhD student working on TEs, trust environments, executions. So yes, we are working on that. We are tagging memory. We are doing different, but that's in development right now, and yes, we are considering that.
Okay, I think there is no more questions. So thank you for your nice presentation, Elkim.
Thank you so much.